Hi, and in today's video, we're gonna go over next gen solar, the Perovskite frontier. Yo, I'm not gonna lie. If there's one video that I have no clue what Jerry is trying to tell me, what? Huh? It's a deep dive into molecular engineering and tandem cell efficiency. Okay, I can understand that, but what? So I might need someone in the comments to teach me this. So what the hold on, let me Perovskite frontier. Maybe during the presentation I'll understand. So this is we're talking about traditional photovoltaics are rapidly approaching the theoretical quasi-chocolate ceiling. And then we have the efficiency leap. And then this tandem cells have shattered single junction records in under a decade. As you can see here, this is like an exponential curve right here. And this is like what silicon was able to, how efficient it was. But now the new perovskite, I don't think I'm saying it right, has like overtaken it. And this is all because of this structure. This is a beautiful structure, though, I'm not gonna lie. So this structure refers to the crystalline structure defined by the general formula ABX₃. Could we stop and just look up? Is this the fourth dimension? I don't know. What's the fourth dimension? How come we don't look in? Yo, what if I go skiing in the third dimension? I saw that like on Instagram and Loki. It looks so sick, bro. But I don't. But that's I'm gonna fall with a VR set on my eyes. Yeah. So by swapping the A cation, the typically methylone ammonium or the X anion halide, scientists can tune the band gap to capture specific wavelengths of light. That's interesting. We have high absorption with 100 times higher absorption coefficient than silicon, and this captures nearly all photons in under 0.5 microns. There's also tunability, with engineered band gaps allow cells to harvest parts of the solar spectrum that silicon simply ignores. There's also low cost, as this solution processing replaces expensive high heat vacuum chambers and pure silicon ignions. The material weight reduction is 99% less active material. Damn. So with the 0.5 micron edge, while a strand of silicon wafer requires 200 microns of thickening to absorb sunlight, I'm gonna just shorten it to PS. The PS film achieves the same result at only 0.5 microns. Dang, wow. This translates to a panel that are 70% lighter and flexible enough to be integrated into building facades. And now we can go into deep dive in tandem cells with layer silicon and perovskite to surpass 33% of PCE lab benchmarks. So we have the hybrid architecture with spectral complementarity. In a tandem configuration, the PS top layer absorbs high energy blue and UV photons. The silicon bottom layer captures the remaining low energy infrared photons. This reduces thermalization loss, maximizes photon to electron conversion, and utilizes existing silicon manufacturing infrastructure. You can look at that graph right here. This is pretty interesting. This is really, I'll give you a minute to like look at it because it is pretty interesting. I'm not gonna lie. Actually, I'm gonna look at it. Let's see. What do we look at? I'm only seeing a lot of colors. I'm not. Guys. Uh, uh, Give me a second. I'll understand it soon. Yep, I understand it. And if you ask me how, we're gonna go on to technology comparison. So we have theoretical max PCE. That's around 29% standard silicon, which is greater than 43% of the next gen tandem. And now the current world record is 26.7% with 34.85% long. I think the lower percentage, the better, I think. That's what it's trying to say. Next, we can talk about manufacturing scale. I don't know why this is so small, but they use a roll-to-roll processing where they move from laboratory spinning coating to industrial scale printing, and the PS ink is applied to flexible substrates in continuous sheets, and this is similar to a newspaper press. And the main challenge remains is stability. Stability? Huh. Well, researchers are now focusing on chemical additives to prevent degradation by moisture and UV exposure. Now, I don't understand that part. That part's pretty interesting. So here's a road for the future of what this looks like. So in 2024, the Longyi breaks efficiency records with 34.8% tandem PCE. Now in 2026, the modern age, the commercial pilot plants begins mass production of 1M times 2M tandem modules. And now in the future, in 2 years, encapsulation breakthroughs expand lifespan to over 20 years. And in 4 years, the tandem P becomes the global standard for high-yield solar farms. Have you ever imagined where we'll be in 4 years? It's crazy to think about. Huh. Okay. That's the end of this video, and this video is mainly about powering the future and discussion of molecular engineering and energy transfer. I think this is an email to learn all about it, but I'm not sure what Jerry's trying to. I'll put in the description of what this is for. But I think it's just an email to understand this more. But here's the image sources. And yeah, if you have any questions or criticisms, just leave it in the comments. And if you ask me comments, I will definitely respond to you, and I would definitely try my best to respond. But yeah, I will see you in a next video, and I hope you learned something cool today. Bye.